In this session, we are discussing the ideas of rotational dynamics as they relate to torque and moment of inertia. We will define in this section the concept of torque and the analog that this is to the linear motion where force is responsible for what we see happening. In the case of rotational motion, torques are responsible for what we see happening. And the response to the torque will be the measured angular acceleration, which is mediated by the moment of inertia, which means that the moment of inertia will reflect the object's resistance to being rotated, and we will have to take that into account as well as we develop a Newtonian second law to use for rotational motion. Now, we studied linear motion, and we developed the concepts of force as they apply to linear acceleration, and we introduced the second law of Newton, F equals ma, and that allowed us to determine momentum, energy, work, power with respect to the motion of an object or the change in the state of motion of that object, and we characterize that motion by the position, the time, the velocity, and the acceleration. So in exactly the same way, we will start out by referring back to the rotational kinematics equations that involve theta and time, as well as omega and alpha. And then, just as we made a direct correspondence in those equations between the linear concepts of x, t, v, and a, as they translate to the rotational kinematics quantities theta, t, omega, and alpha, we will also do a similar correspondence with respect to rotational dynamics. First of all, in linear motion, we were looking strictly at forces that pass through the center of mass of the object. In other words, the line of action of this force passes directly through the center of mass, and the only influence that that force can impart to that mass is straight line motion through the center of mass. This force will not cause the object to rotate. And these are referred to as concurrent forces. Now we want to expand our analysis so we can allow this force to move away from the center of mass so that its line of action passes through a point which is not passing through the center of mass, and therefore this force will result in rotational motion. Shown in this slide is an applied force whose line of action, the dotted line, is passing through a point not at the center of mass of this object. And in this object, the geometrical center of mass would be right here. So the result of this force will be to rotate this object. And we call forces that do not pass through the center of mass non-concurrent forces. And non-concurrent forces are responsible for rotational motion. The rotational influence that results from this non-concurrent force is called torque. Torque is the analog of force in linear motion. In other words, where we had force in linear motion responsible for linear acceleration, we will now have torque in rotational motion responsible for rotational acceleration. But we need to define the torque first. So we use the symbol for torque, tau, the lowercase t in the Greek alphabet. So tau is our symbol for torque, and it's defined according to the distance from the point of rotation screen popped up. The distance from the point of rotation is r, so if we're rotating about the center of mass of this object, then we go from that center of mass to the point where the force, the line of action of the force, intersects. Notice that the force in this case is at an angle to that distance r. If you extend the line r out, you get this dashed line. And if you extend the force line along its line of action backwards, you get that line. And the angle we're talking about is the angle between the direction of the force and the direction of the lever arm, as it's referred to often. So the product of r, the magnitude of r, times the magnitude of f, times the sine of the angle between those two vectors is the magnitude of the torque. Now in this particular diagram, if you take your right hand and you turn your fingers, curl your fingers in a clockwise direction, in essence pointing along the direction of r, and then turning your fingers toward the direction of f, you find that your thumb will be pointing directly into the board. This is a right-hand rule that we use to try to illustrate the direction that we will apply to this torque. Because remember, torque is a vector. And this calculation here is for the magnitude of that vector, but the direction of that vector will be the direction your thumb is pointing in. And so by pointing your fingers along the direction of r and turning them toward f, your thumb goes into the board. Your hand turns in a clockwise manner, your thumb into the board, and therefore we refer to this as a negative or clockwise torque. So we're going to be dealing with torques that are clockwise, and that vector direction will be negative, and counterclockwise, and that direction will be positive. Think about when you take a screwdriver and you are tightening a screw, putting a screw in a board or something. You are rotating the screwdriver clockwise to push it in, to screw it in, and counterclockwise for it to come out. So clockwise in, away from you, negative, counterclockwise out, toward you, positive. So what we have here, the units on torque are Newton meters. The units, of course, on the distance r, the lever arm, and the force F. Clockwise torques will be designated as negative. Counterclockwise torques will be designated as positive. Torque is a vector. So the vector directions we'll be dealing with either will be plus or minus as we deal with planar torques. The sum of the torques then, just like in Newton's second law with the sum of the forces, the sum of the torques is going to be referred to as the net torque. In other words, you may have forces applied to an object that want to influence it to rotate clockwise, and other forces applied that want to influence it to rotate counterclockwise. And so we're going to take those positive counterclockwise torques, subtract the negative clockwise torques, and we'll have a remaining net torque that's responsible for the rotational motion. Net torque results in rotational or angular acceleration. We know what angular acceleration is. It's our term alpha, which is the rate of change of angular velocity. The amount of the angular acceleration that's imparted depends upon the location of the forces, which means the size of the torques that are applied. It also depends upon the shape of the object, or another way to say that is how the mass is distributed relative to the point of rotation. Let's derive a second law equivalent for rotation that we can use, just like we used in linear motion. We had F equals ma. We want an equation that now relates the rotational influence to the rotational effect. And to do that, we'll start with Newton's second law, because we know this equation is a valid equation. Now we'll manipulate this a little bit. If we start with this equation, F equals ma, and let's multiply both sides by r. So we get an r times the F and an r times the ma term. We just got done defining a term r times F as the torque, And in this case, if we restrict ourselves to a force that is perpendicular to the lever arm R, then the sine of the angle theta will be sine of 90, and sine of 90 is 1. Also, if we let the product A times R, you might recall that in our session where we looked at linear and rotational motion, we defined that term as the angular acceleration alpha, and so we substitute A times R equals alpha, and we have the remaining term mr squared times alpha, and we identify I as the product of mr squared, so we have the final result. The torque is the moment of inertia times the angular acceleration. The moment of inertia was the combination of symbols m times r squared. In this case, we were simply dealing with one mass with a force applied to that mass, and that mass was displaced from the point of rotation by a distance r. So this is a general equation. It tells us that the torque acting on this object, whose moment of inertia is I, which we'll calculate in a moment, results in that object acquiring an angular acceleration of alpha. So that equation at the top shows you that we're dealing again with the net torque. In other words, the previous slide didn't specify that there were more than one torques, but now we want to expand this to specify that we can have positive and negative torques. And so we're really only interested in what is the remaining total torque after we've subtracted the clockwise from the counterclockwise torques. And that's what's responsible for the object whose moment of inertia is I, acquiring an angular acceleration alpha. Now we need to talk a little bit about the moment of inertia, because that relates to how the mass is located relative to the point at which we're rotating about. So let's start with a model of two masses, shown here, connected by a thin light rod. The thin light rod merely means that we don't need to include its mass in our calculation, that it is negligibly small, and in fact we can essentially make its mass equal to 0. We want to rotate this object about this axis, this vertical axis, halfway between the two masses. Now, these masses, that point of rotation specifies now that the masses are on the right and left side of this point of rotation. If we had chosen that vertical line to be located on one of the masses, that would have changed the situation. So notice that where we place this vertical line determines where the masses are located relative to it. And that means that the moment of inertia is going to change depending upon where the axis of rotation is located. But in this case, we are trying to find out what is the moment of inertia in this situation with the line of rotation, or the axis of rotation, midway between. What we are actually determining is the resistance of this object to being rotated. That's what inertia refers to, the resistance to change, and this is rotational inertia, called the moment of inertia, so this is the resistance to being rotationally accelerated. And you can see that just like inertia in linear motion, it is dependent upon the mass, but now it's also dependent upon how that mass is located relative to the axis that we're spinning about. And location means distance r from that point of rotation. We define the moment of inertia for a point mass system as the summation of the individual masses times their distance squared from the point of rotation. So mi stands for each mass, m1 for mass 1, located at r1, which we square in our definition of moment of inertia, plus the second term m2 r2 squared. So as you can see, if the axis of rotation moves, then the values of R1 and R2 change, and therefore the calculation of I changes as well. So this is a formula that we can use to calculate the moment of inertia for a distribution of point masses. So that tells us that because the moment of inertia depends upon the location of the axis of rotation, then there's not just one moment of inertia. It'll be different for every axis we choose. M, the mass, is part of the moment of inertia because the mass is a measure of the resistance of an object to being linearly accelerated, and in this case then, along with the distance from the axis of rotation, those two terms give us the measure of the object's resistance to being rotated. It takes into account its shape as well as its mass. Objects that are located right on the axis of rotation will have no distance from that axis, r equals 0, so they won't contribute to the moment of inertia. And again, if you remember what the concept of inertia for linear motion, inertia is an expression of the resistance to being accelerated. In this case, I is an expression of the difficulty in causing the object to rotate with an angular acceleration. Now, most objects, such as the chair you're sitting in, or a book or a table, are continuous objects, not point masses, and so we need to have a way of calculating their moments of inertia according to their continuous distribution rather than a discrete point-like distribution. Well, that would involve some calculus, and we're not going to do that. We're going to simply refer you to the table in your book that lists some common moments of inertia for objects that we will be using in our homework problems. So these are listed in tables and have already been determined. For instance, you'll notice that for a sphere, and this is a solid sphere, the moment of inertia is 2/5 times mr squared. So there's the mr squared term. We know that should be there. That's the mass times the product of a distance squared. So it's got the right units for moment of inertia, which is kilogram meter squared. You notice that the term changes. The coefficient will change to 1/2 if we're talking about a solid disk rotating about its center, or a hoop, like a ring, rotating about its center. The coefficient is 1. Or if we have a spherical shell rotating about its center, then instead of 2/5, it'll be 2/3. So these calculations have already been done for these common objects, and we can simply use them in our problems. If the problem states that a solid sphere is rolling down an inclined plane, then we know we have to incorporate the moment of inertia of the solid sphere, which is 2/5 mr squared. So finally, we've identified a rotational force law. This is the analog to Newton's second law from linear motion. Now we have one for rotational motion. And it says that the net torque applied to an object whose moment of inertia is I will be responsible for causing that object to rotate with an angular acceleration of alpha. So just as we did with linear motion, the first thing we might want to do is identify the torques acting on an object, because that's the same as creating our free body diagram, placing the forces on that object, identifying their lever arms from their point of rotation to the application of the force, determining the torque then, and then adding up the clockwise ones and subtracting the adding up the counterclockwise ones and subtracting the clockwise ones, and finding the net torque acting on the object. If the object is a continuous object, we'll look up our moment of inertia formula. and calculate that, or if it's a point-like object, we'll calculate it from the summation of mr squared. And then we'll have the torque, and we'll have the moment of inertia, and we can then find the angular acceleration that this object will experience. And then from that, we can go back to our rotational kinematics formulas and determine what the object's angular velocity is, what its angular position is at whatever time we're dealing with. So we're going to use this rotational force law just as we did with linear motion, where we described linear kinematics and then we introduced Newton's second law. Now we've also described rotational kinematics and introduced this Newtonian second law for rotation. Thank you.